So I want you to imagine, just for a second, a truly daunting medical challenge. Like, imagine you are a pathologist, right?
Okay, yeah.
You are looking at a tiny digitized slice of human tissue on a computer screen. And from that microscopic landscape, which is really just this chaotic jumble of pink and purple shapes, cell walls, nuclei, you are asked to predict a patient's exact future.
Which is an incredible amount of pressure, right?
Exactly. You literally have to predict whether they will survive the next 5 years.
Yeah, we are basically asking human eyes to see the invisible rules of biology playing out in a frozen moment in time. Because a single whole slide image of a biopsy, I mean, it can contain billions of pixels.
Wow, billions.
Oh, yeah. Finding the prognostic clues in there is like, well, it's like searching for a specific sentence in a massive library of unindexed books.
That's wild. But today, we are taking a deep dive into a groundbreaking research paper that is actually trying to solve this exact problem specifically for colorectal cancer.
Which is a huge deal.
It is. The paper introduces this AI framework called MorphDistill. And the mission of our deep dive today is to really unpack how researchers have managed to take 10 different massive artificial intelligence models and somehow squeeze all of their collective brain power into one hyper-efficient tool.
And this tool predicts cancer survival, which is just fascinating.
Right. And the context of why this research focuses on colorectal cancer, or CRC, is pretty crucial for you to understand.
Yeah, I mean, CRC remains a leading cause of cancer mortality worldwide. Epidemiological projections show a potential 60% increase in cases by 2030.
Wait, 60%? That's massive.
Yeah, it translates to an estimated 2.2 million new cases annually. So the sheer volume of patients requiring incredibly complex prognostic evaluations is basically going to overwhelm our current medical infrastructure.
And predicting survival for these patients is notoriously hard anyway, because the tumors themselves are so physically varied. The paper actually refers to this as morphological heterogeneity.
Right, which basically means no two tumors look the same.
Yeah, every tumor is like a unique, chaotic fingerprint.
Exactly. And conventional histopathological assessment, which just means a human doctor looking through the microscope and grading the tissue based on established criteria, it really only captures a fraction of the prognostic info hidden in that tissue.
Because humans just can't process that much raw data.
Right. Human cognition simply cannot weigh thousands of subtle structural variations simultaneously, to put a precise survival probability.
Okay, let's unpack this, because to understand how MorphDistill solves this massive bottleneck, we first need to understand why our current, most advanced AI isn't already cutting it.
Yeah, so the current gold standard in computational pathology relies on what we call foundation models. And the paper examines a few of these with names like UNIV2, GigaPath, or 𝗔
Okay.
These are massive artificial intelligence networks that have been trained via self-supervised learning on millions, sometimes hundreds of millions, of tissue slides.
So they've been fed an unfathomable amount of medical data. I mean, they should be the ultimate experts, right?
You would think so. They are incredibly sophisticated, but they suffer from a very specific limitation. Because they're trained on such vast, diverse data sets, everything from brain tissue to lung tissue to skin, they are what we call domain agnostic.
Oh, I see. So they are generalists.
Exactly.
They know a little bit about everything, but they haven't spent their whole lives studying just the colon.
Right. They might be fantastic at recognizing a generic cell structure, but they routinely overlook highly specific colorectal cancer features. Take something called a desmoplastic stromal reaction, for example.
A desmoplastic? Wait, what is that?
It's a specific type of dense, fibrous, basically scar-like tissue that forms around an invasive tumor. Or consider tumor budding, where single cancer cells, or tiny clusters, basically break off from the main tumor mass and start invading the surrounding tissue.
Oh, wow. So if an AI isn't specifically tuned to look for a tiny cluster of breakaway cells, it might just classify it as generic background noise?
Yeah, exactly. And those specific features are absolutely critical for predicting if a CRC patient will survive. A generalist foundation model might basically miss the forest for the trees. Or in this case, miss the deadly breakaway cells for the generic pink tissue.
That makes total sense. But the paper points out another major hurdle, right? There isn't just one of these foundation models.
No, there are dozens.
Yeah, like UNIV2 captures one aspect of tissue morphology. GigaPath is built differently and captures another. 𝗠ci captures something else entirely.
Right.
So we have all these different AI brains, but they have completely different underlying architectures. The paper states they operate in different mathematical dimensions.
Yeah, and to understand this barrier, you really have to look at how AI actually sees an image. When one of these models looks at a tiny square of tissue, it doesn't see a picture like we do.
It just sees data.
Right. It runs that picture through its neural network and translates it into a massive list of numbers, which we call a vector, or an embedding.
So it's turning a visual of a cancer cell into pure math.
Exactly. One model, like GigaPath, might describe that tissue patch using a list of 1,536 numbers. But another model, like 𝗠ci, might describe the exact same tissue patch using a list of only 512 numbers.
Oh, I get it. So they are mathematically incompatible.
Completely.
Yeah.
You cannot simply merge a 1,536-dimensional space with a 512-dimensional space.
It's like having 10 brilliant doctors who all speak completely different, untranslatable languages. You know, you have the French doctor who only looks at the stroma, the Japanese doctor who only looks at immune cells, and you just can't get them to talk to each other to form a consensus.
That is a perfect analogy.
But I have to push back on the premise of this paper because this seems like an impossible engineering problem. If no single model is good enough, but they all speak completely different structural languages, how do you combine them without just creating a bloated, computationally impossible mess of data?
Yeah, this gets to the absolute core of the Tower of Babel problem in medical AI, right? Unifying disparate, dimensionally incompatible data requires rethinking how AI models communicate entirely.
Okay, so what did they do?
Yeah, the researchers bypassed the language barrier entirely, using a mathematical technique called dimension-agnostic relational alignment.
Dimension-agnostic relational alignment. I actually love this concept. Let me try to break this down for you with an analogy.
Go for it.
Imagine you have 10 movie critics. These are our 10 teacher models. You want to combine all their opinions into one ultimate master guide. But critic A uses a 5-star scale. Critic B uses a scale of 1 to 100. Critic C just gives a thumbs up or thumbs down.
Right, the scales don't match.
Exactly. If you try to mathematically average a 4 stars with a thumbs up, the math just breaks. It's total nonsense.
Because the underlying dimensions of their rating systems do not align.
Right. So instead of forcing all 10 movie critics to use the exact same rating scale instead of trying to map their specific features, MorphDistill just looks at which movies they put in the same pile.
Ah, I see.
Yeah. If all 10 critics group The Godfather and Goodfellas closely together, the student AI learns, okay, these two things belong near each other. MorphDistill doesn't match the specific feature data. It matches the neighborhood structures. It watches how the teacher models group similar tissue patches together.
That's a really great way to put it. In the actual framework, the researchers take 10 of these massive foundation models, so the teachers, and use them to train one compact student model.
Okay.
They start by normalizing the embeddings from each teacher, kind of standardizing the scale. Then they compute pairwise similarities within a batch of tissue patches.
Oh, so they ask the models to compare notes relative to their own languages?
Basically, yeah. They're essentially asking, hey teacher, in your unique 1,536-dimensional space, how similar is patch A to patch B? And the teacher outputs a probability score.
Got it.
Then the student model, which operates in its own completely separate dimension, is trained to mimic that probability score. It learns the relationships, not the raw data.
And the paper mentions something called a temperature parameter that helps control this matching process, right?
Yeah, so converting raw similarity scores into probability distributions involves this temperature setting in the mathematical equations. It acts kind of like a focus dial.
Like a camera lens.
Yeah. Higher temperatures capture broad relational patterns, the soft relationships, like understanding that a rom-com and a drama are both movies, even if they aren't the same genre. Lower temperatures sharpen the focus on exact nearest neighbors, realizing that two specific action movies are nearly identical.
So the student model absorbs the consensus of the group dynamics, and it preserves the representational geometry of all 10 teachers without forcing them into the same shape.
Exactly.
Like if one teacher spots that subtle tumor budding we talked about earlier, the student feels the mathematical pull of that teacher's similarity distribution and just preserves that structure.
Right. And the elegance of it is in its efficiency. It synthesizes the collective intelligence of 10 massive neural networks without inheriting their immense computational bulk.
But here's where it gets really interesting, because grouping things together based on the teacher's vibes is a great mathematical trick.
Sure.
But to be useful to a pathologist in a hospital, the AI actually has to know what it's looking at in the real world. I mean, it can't just say, oh, these pink blobs are mathematically similar. It needs to know this is a tumor and this is healthy tissue.
Right. The relational distillation we just discussed floats in a bit of an abstract space. So to anchor it, the researchers introduced a second mechanism during the training phase.
Okay.
It's called supervised contrastive regularization.
Okay, so they grounded the math using real human biology. They used 3 massive, meticulously labeled data sets to train the student, CRC-100K, STARK9, and SPIDER.
Yes.
And together, these data sets encompass 18 distinct colorectal tissue classes.
Right, and we're talking about highly specific biological markers here. Adipose tissue, which is fat. Lymphocytes, which are white blood cells indicating an immune response. Adenocarcinoma, which is the actual glandular cancer. They even labeled necrosis.
Necrosis meaning dead tissue.
Dead cell tissue, yes. In the context of a tumor, necrosis often indicates that the cancer is growing so rapidly and aggressively that it has actually outgrown its own blood supply.
Oh, wow.
Yeah, causing the center of the tumor to die. It is a highly relevant prognostic indicator.
So by feeding the AI these 18 classes, they basically force it to learn the vocabulary of colorectal cancer.
Exactly.
And when you look at the TSNE visualizations in the paper, for those listening, these are maps that show how the AI organizes info in its brain. The impact is undeniable.
Oh, the maps are beautiful. The objective function of this supervised training literally pulls the mathematical embeddings of patches from the same tissue class tightly together.
And pushes the others away.
Yes, violently pushes embeddings from different classes apart.
Yeah, the maps are incredible. Like when you look at the older foundation models, the tissue classes are kind of smeared together. The border between a lymphocyte and a tumor cell is fuzzy. But with MorphDistill, you see incredibly compact, clearly separated clusters. The paper shows these colorful patch-level classification maps where the AI perfectly delineates the tumor from the stroma, from the healthy tissue, right there on the biopsy slide.
It really is striking.
It looks like a pristine paint-by-numbers of cancer biology.
And this step ensures that the dimension-agnostic math isn't just a clever exercise. The model is rigidly forced to focus on the morphological heterogeneity that actually matters for survival prediction.
So we have a brilliantly organized map of tissue. The AI knows what everything is, and it has the combined wisdom of 10 different models.
Yep.
But a map isn't a diagnosis. How do we take this beautifully sorted biology and actually predict if a patient has 5 years to live?
Right. So here's the second stage. The researchers basically freeze the trained MorphDistill encoder. Its understanding of tissue is set in stone.
Okay.
They then use it to extract features from a patient's whole slide image. The encoder transforms the massive digital slide into a bag of individual patch-level embeddings.
And a whole slide image can have thousands of these little patches.
That's thousands of data points per patient. So to make sense of them all, the researchers employ an attention-based multiple instance learning system, or ABEL.
Okay, I understand the concept of multiple instance learning, like looking at all the patches to make one unified decision. But how does the AI know what to actually pay attention to? Because a lot of that slide is just going to be normal, healthy colon tissue.
That's where the attention mechanism comes in. It functions like a weighting system. During the training of this predictive stage, the algorithm learns which tissue patterns actually correlate with poor outcomes.
Oh, okay.
It learns to ignore the vast expanses of healthy tissue and assigns heavy mathematical weight to the dangerous neighborhoods.
Oh, so it zeroes in on the invasive tumor front, or like the areas where the immune system is actively fighting the cancer?
Exactly. It aggregates all that weighted info to output a single binary prediction. Will this patient survive beyond 5 years?
And the stats on this predictive test are what make the paper so compelling to me. They ran this on a clinical trial cohort called Alliance CLGB-89803.
Right.
This featured 424 stage 3 colorectal cancer patients, and crucially, they had the long-term follow-up data to know what actually happened to these people in real life. And MorphDistill achieved an AUC of 0.68.
Which is huge.
Yeah.
For context, the best individual foundation model tested, UNIV2, only hit an AUC of 0.63.
Let's translate AUC, or area under the curve, for a second. Think of it as a reliability grade for a test, where guessing randomly gets you a 0.50, like flipping a coin.
Right.
An AUC of 1.0 means the test is perfect every single time. So jumping from 0.63 to 0.68 might sound like a tiny fraction, but in the world of predicting human biology, an 8% relative improvement over the state-of-the-art is massive.
It really represents a significant lead in predictive capability. And the clinical utility becomes even clearer when you look at the risk stratification. They calculated a hazard ratio of 2.52.
Meaning that patients flagged as high risk by MorphDistill are over 2.5 times more likely to pass away within 5 years compared to the patients it flagged as low risk.
Exactly. The model creates a stark, distinct separation between patient outcomes based solely on the visual morphology of their tissue.
I need to play devil's advocate here, though.
Uh-oh.
Because the history of medical AI is literally littered with models that look great on paper but completely fail in the real world.
That's very true.
Like, sure, it works beautifully on one specific clinical trial, but trials are highly controlled environments. Patients in trials are often subjected to very specific treatment protocols. So how do we know that AI isn't just memorizing the quirks of the data? For example, what if it only predicts well for patients given a very specific type of chemotherapy?
Yeah, that's overfitting. Where an AI memorizes the training data rather than learning the underlying biological rules, it's basically the most persistent threat in computational pathology.
Yeah.
But the researchers anticipated this exact critique. They actually performed a stratified analysis within the trial cohort, specifically looking at different chemotherapy regimens.
The trial used FL versus IFL treatments, right?
Yes. And MorphDistill's performance remained remarkably stable across both. It achieved an AUC of 0.70 for the FL group and 0.65 for the IFL group.
So it's not just recognizing a biological reaction to one specific drug.
No, not at all. And they applied the same rigorous stratification to other variables. They checked performance across sexes, achieving comparable predictive power for both male and female patients.
That's good.
They analyzed tumor location, too. Whether the tumor was located in the cecum on the right side of the colon or the splenic flexure on the left side, the model maintained its accuracy.
But let's talk about the microscopes in the hospitals themselves, because a huge problem with AI is that a hospital in London might use a slightly different chemical stain or a different brand of digital scanner than a clinic in Boston.
Oh, the batch effect, yes.
Yeah, the AI might learn that pinkish purple from Boston means high risk, rather than actually looking at the cancer.
Did they test this outside of that single trial specific laboratory setup?
They did. They subjected MorphDistill to an external validation using an entirely separate dataset, the TCGA cohort.
Right.
This included 562 patients from multiple different institutions. So this means different digital scanners, different patient populations, and completely different slide preparation protocols.
Basically the ultimate stress test for an AI's robustness.
Exactly. And MorphDistill still outperformed 5 established multiple instance learning methods on this disparate data. It achieved a concordance index of 0.615.
And the concordance index is another reliability score, right?
Mm-hmm.
Specifically used in survival analysis to measure how well a model ranks patients by their risk.
Yep.
So beating the baselines on external data proves a fundamental point. It proves the model is learning universal cancer biology. It is capturing the intrinsic morphological characteristics of colorectal cancer that generalize across diverse clinical settings, rather than just memorizing the microscopic color balance of one specific hospital's laboratory.
So what does this all mean? We have an AI that is highly accurate. It avoids the pitfalls of overfitting. It generalizes across different hospitals, but is it actually practical?
That's the real question.
Right, because if you are running a busy hospital pathology department, you can't wait 3 days for a supercomputer to process one patient's biopsy slide. And the ablation study in the paper reveals what is honestly the most surprising finding of this whole deep dive.
Yeah, the distillation process yields a profound advantage in computational efficiency. Despite containing the synthesized knowledge of 10 massive foundation models, MorphDistill itself is incredibly lightweight.
Yeah, the student model only has 86 million parameters.
To put that in perspective, one of its teachers, the 𝗤𝗄𝗵𝗵𝗵𝗵 model, operates with 1.1 billion parameters. The student is a tiny fraction of the size of just a single teacher.
That's crazy. And because it's so incredibly compact, it processes 1,000 tissue patches in just 1.5 seconds.
Wow.
The paper notes that is a 2.04x speedup over the average foundation model. It's literally twice as fast as the AI it learned from.
Which is the defining factor for clinical deployment. Whole slide images are gigabytes of data per patient.
Right.
Processing thousands of patches per slide at high speed means this framework can actually be integrated into a high-throughput clinical workflow using standard hospital computers. You don't need million-dollar server farms to run this.
Let's bring this all the way back to the patient sitting in the doctor's office, waiting for their biopsy results. Why does this combination of speed, accuracy, and AI distillation actually matter to their life?
Well, in a clinical setting, predicting 5-year survival for stage 3 colorectal cancer directly dictates the course of adjuvant therapy. It determines what happens after the surgeon removes the primary tumor.
So it determines the chemotherapy decisions.
Exactly. And chemotherapy is inherently toxic. It comes with severe, sometimes lifelong side effects. Fast, highly accurate risk stratification means oncologists can confidently spare low-risk patients the severe toxicities of aggressive, heavy-hitting chemotherapy regimens.
So if the AI looks at the tissue and says the neighborhood is safe, you don't drop a bomb on it.
Right. You don't overtreat. Conversely, it ensures that high-risk patients, the ones whose tissue hides those subtle, dangerous morphological clues that a human eye might miss, they get the aggressive, targeted treatments they desperately need immediately.
It's like a paradigm shift.
It is. It shifts the paradigm to true precision medicine, personalized to the exact biological geometry of the patient's tumor.
It's precision medicine powered by the consensus of 10 AI minds acting as one. I love that. Let's take a breath and just recap this incredible journey.
Sure.
We started with the chaotic, multilingual world of massive AI foundation models.
Yeah.
You know, the whole Tower of Babel problem. We explored how the researchers used dimension-agnostic relational distillation to bypass the language barrier, training a student AI to match neighborhood relationships rather than incompatible data lists.
Yes.
And then we saw how they grounded that abstract math in real colorectal tissue data, creating a fast, lightweight, highly accurate survival predictor that holds its ground against the messy realities of real-world clinical trials and diverse hospital data.
It is a profound demonstration of not reinventing the wheel, but rather engineering a system where all the existing wheels turn together in perfect synchrony.
It really is, and we've spent this entire time exploring how MorphDistill successfully used this dimension-agnostic math to combine visual models, right? Models that look at literal pictures of human tissue.
Yeah.
But reading this paper made me wonder about the ultimate ceiling of this technology. If the math just looks at abstract relationships, like how things are grouped together, it fundamentally doesn't care if the input is an image.
Right.
So how far can we push this framework?
Oh, that question points toward the most exciting frontier in medical AI. I mean, think about the implications of dimension-agnostic alignment. What if we applied this exact same mathematical framework to entirely different senses or fields of medicine?
Wait, like what?
Could we use relational distillation to build an AI that concurrently groups visual tissue patterns from a slide, the intricate sequences of a patient's genomic DNA, and the written text of their clinical history?
Oh my gosh.
Right. Could this framework be the blueprint for a multisensory AI diagnostician that finally connects all the disparate medical dots into one unified understanding of a patient's health.
That is wild. It's incredible to think that the mathematical blueprint for that kind of multisensory medical future might start with just trying to predict survival from one tiny, chaotic slice of digitized tissue on a screen.
It really puts it in perspective.
It does. Thank you for joining us on this deep dive. Keep asking questions, keep wondering, and we'll see you next time.